energy in your body to actually do stuff. And so again, if you are going and creating bonds, you're storing it. If you're breaking bonds, you're using it, and that's all it comes down to. So the video that's on there is just going to be all about energy and chemistry. And so this one is just going to explain some of the stuff you already know and how, kinetic energy is, again, energy of motion. Potential energy is just storing all that energy. So this stuff you've already gone over before. So this idea of oxidation and reduction reactions are exactly similar to the idea of going and having kinetic and potential energy. So oxidation and reduction reactions, we call them redox reactions. They are used in a very high quantity when storing bonds or breaking bonds. So energy is going to be transferred from one molecule to another via redox reactions. So in other words, one molecule will gain something, one molecule will lose something, similar to like ionic bonds. Covalent bonds, they generally share it, but honestly still one is going to be giving up over the other. If you're going and even drawing Lewis diagrams, you kind of have an idea of that. And so again, we've gone over before, but oxidation is when an atom loses an electron, and reduction is when it's going to gain an electron. And so again, we call it reducing because it reduces the charge. So if you had a -1 and you add an electron, now it's a -2. So it's going to reduce the charge even further and make it more electronegative. And so oxidation is the opposite, and that's when you're losing the electrons and you're going to be more positive. Almost everything in chapter 7, 8, and 7 and 8 are going to be all about redox reactions for your metabolism, for your cellular respiration, and then also for photosynthesis. So it's kind of like a term we'll just get used to. But something that has a reducing power, that's going to be the ability of organisms to store energy in molecules by transferring electrons to them. And all living things have to do this to store energy. So again, a reducing power is just the ability of organisms to store energy in molecules by going and transferring electrons to them in some way, shape, or form. And again, I just want to make sure you have this. So again, reducing power is just the ability of organisms to go and store energy in molecules by transferring electrons to them. And again, it's very important to living things. So if you want to be able to have any type of metabolism, this is what you're going to end up needing. And so again, it's just a simple fact that you're going to be going and transferring this type of thing, these electrons. And so again, loss of an electron is oxidation, gain is going to be reduction because you're reducing the charge. Reducing power is just the ability of this to be taking place in the first place, so you can transfer energy for something else.
Wait, it's the ability of organisms to store energy in molecules and liquids?
Just to basically transfer the energy back and forth between them. So,
So like when someone has fast metabolism, is it because there's like an increase or?
Yeah, they usually have more enzymes, in other words, to actually go and do all of the reactions, and someone that has less would not be able to do as much.
Okay.
You actually usually inherit your metabolism from your female, so from your mom, because your mitochondria are from your mom. So if she has genetic disorders from their mitochondria, you will also have genetic disorders from your mitochondria. So regardless of you are a female or a male, that's who you inherit it from. Because eggs are like this big in comparison to like sperm is this tiny. So there's like nothing in the sperm except DNA of genetic material. So mitochondria and all of your organelles are replicated from the female instead. So like all of your DNA inside your mitochondria, all from mom. And so always pay attention to the mom's metabolism. So if your dad's is fast, doesn't matter. If your mom's is really slow, that's the one you're getting. And so that will work for regardless of whatever her children are, because you inherit their DNA from the mitochondria. So this you also know, the law of thermodynamics, but the second one we're just going to apply to, again, the idea of like energy. So the first law of thermodynamics, you know this. Energy cannot be created nor destroyed, or at least you should have covered this. So again, you cannot go and create or destroy energy. You can only change it from one form to another, like potential to kinetic, kinetic to potential, or something like that. A lion eating a giraffe, a plant using light energy. You're just taking that energy to make something. You're breaking down food to make energy. And so again, energy cannot be created nor destroyed. It can only change from one form to another, or from a gas to a liquid to a solid. Like you're changing the state in some way, shape, or form, but you just can't create it out of anywhere. So that's not how it works. So again, energy cannot be created nor destroyed. It can just be transformed in some way, shape, or form. And so again, a lion eating a giraffe, you're eating the giraffe, you're gaining the energy from it, and now you're creating the chemical bonds. Same thing for plant energy. You're going to be able to go and take in the sunlight, and you're converting that sunlight and those photons into the ability to charge the area to make the chloroplast, function, and now you can go and again create technically energy and things like that. So same general idea. So chemical potential energy is within the body you can convert to other forms. So in other words, if you eat something that's a fat, it doesn't mean you're creating fat. You can actually create other things within your body. You're breaking down those fats for energy. It's beta oxidation. If you are going to be going and breaking down sugars, cellular respiration. If you're going to be breaking down proteins, deamination. We'll be covering all of this in chapter 7. You don't have to know the words for now. Just know simply that with chemical potential energy, that's the food you're putting in your mouth. And so that's going to be when your body converts it to other forms of energy. So you're taking those solids and you're making it into something that's going to be ATP, which is energy. So you cannot survive without energy in your body. So some of the energy that's not going to be used is dissipated as heat. If you go and take your temperature when you're going and eating food versus just in a resting state, completely different temperature by a few degrees, because your body heats up when you're going to consume food. It can also make you a little bit tired at first too. And so again, anytime you're going to break something down, you're not going to get 100% of it out of there. It's going to be some waste. So some of that waste is usually heat energy. And so it will come off as that. And so again, technically this what they're trying to show you is you can start with a certain amount of energy, it can go through a transformation process, and now it will look like something different. So if you're eating a hamburger, it's going to slowly go through you, you can get ATP and energy from it, and then you also might have heat be dissipated as well in this process. And so again, you're not necessarily always going to have exactly 100% of what you put in, 100% of what you come out. There's going to be some type of waste. Think of even when you're boiling water and you're going to go and again have the water go from, let's say, a colder state to a hotter state and it begins boiling and you're going to turn it into a gas. Not everything is going to be completely converted perfect. There's going to be what we call some disorder in the systems that's going to lead to not 100% happening, and that's what this is about. So entropy is just the idea that there's always going to be some form of disorder in a system. I mean, think about it. If you eat food, you do have waste. You have feces come out of you. That means that you did not convert 100% of the food you ate. Some of it you couldn't do, so that's what came out the other end. And so some of it could not be broken down, especially cellulose. So anytime, it's just the idea of anytime you're going to have any reaction, there's going to be some type of disorder in the system. So the universe is continuously increasing. Random molecule motion is always going to end up happening. You're going to have some type of waste product. So you are not always going to have, again, the same exact thing coming out of this system. There will only be some usable energy and some unusable energy afterwards when you're doing a transformation. That is what literally your poop is. Your pee is something different, but it's still considered somewhat of a waste. And so either way, entropy is just a measure of the disorder in a system. Think of just, okay, you take a pile of bricks that's perfectly stacked on top of a roof. You throw them off the roof. The chance of them falling perfectly stacked with no chip marks is like near impossible. Never 100%, but it's, 0.00001 chance of happening. And so because of that, we would say the disorder in the system is when they're lying all over the ground because they're not going to be perfect. They're not going to have, every single little mark not be on them. They're not going to be chipped. The chances of that happening is very rare. And so again, there will be some form of disorder. You have a lot of waste when you go and you actually break chemical bonds down. Even when you make things, you're going to have waste too. That's going to be, coming of it. And we will discuss that when we talk about the Krebs cycle. And so again, entropy is just the measure of disorder in the system. The example is just the idea of a brick that, again, if you go and you throw them off a roof, they're not going to stack perfect. They're going to be all over the ground, or a few might stack, some might get chipped, some are going to be broken into pieces, and so there is disorder. You cannot convert everything perfect. Just like when you consume food, you're going to have waste. You're going to have an excretory system.
Can you go over the second law of thermodynamics, like definition of it?
Just simply the fact that entropy exists in any of these reactions. So you will never have 100% taken out of a reaction that you put in. There's always going to be some form of what we call disorder. So again, disorder is just going to be entropy. So the second law of thermodynamics is just simply saying that whenever you're transferring or transforming any type of energy, there'll be some type of disorder in the system. And so there will be some type of unusable energy. It's never going to be just 100% and that's it. And so this is what it's basically trying to tell you. So this is the whole idea of free energy, which you might have covered, I don't know, sometimes what you get up to in chemistry or in physics. But free energy, this is the amount of energy actually available to break and subsequently form other chemical bonds. So this is the available energy to do something with inside your body. And so you created this, it is extra. Remember, if you have too much free energy, what do you think turns into fats? So that's why there's a certain amount of usable energy, that's what calories are that you get from food. And so if you eat too many calories, it turns into a fat instead of going and being broken down. That's the whole idea of this. So free energy is represented by G. And so again, the amount of energy actually available to break and subsequently form other chemical bonds, that's the free energy. You can use it for something. It's not being used in your body for just even, pumping your heart or making me talk right now. You're using it for something else. And so again, free energy is the amount of energy actually available to break and subsequently form other chemical bonds. So, when you do the equation, this is the way I think of it. So technically H is going to stand for something that's called enthalpy. I think I put the word on there so you should have it. It's the one that's E-N-T-H-A-L-P-Y. So that's going to be enthalpy. That's what H stands for. This is the energy contained in a molecule's chemical bonds. So in other words, if you are going to go and you are now going to have a lovely hamburger, and this is what you're eating, that's going to be your H. So just think hamburger is the way I put it. So this is going to be something that you're going to put in here. This is going to be your food. So something that you are going to be going and putting inside your mouth and eating and breaking down for energy, that is going to be technically what you'll have for H. H doesn't mean hamburger. H stands for enthalpy, but it's just an easier way to remember this stuff. So what you're going to do is your body will go through all these processes to break things down, and so it's going to do this at a very specific temperature. And so whatever the T stands for, this will be the temperature that this is all going to be occurring in. Remember, the hotter the temperature, the faster you break things down. The lower the temperature, the slower you break them down. But again, remember, your enzymes are very specific to the temperature they like. That's what that lab's going to be about, is how temperature and pH affects it. There is going to be a point where too hot is a problem. And so again, usually in human bodies, in adults after 104 degrees, you got a problem. After children, 105 degrees, you have a problem. Things just don't start working the same. And so again, T is going to be any temperature this is happening at, and usually it's going to be in kelvins. And so this will be usually the way we measure it, not in Celsius or Fahrenheit. So S is going to be the one next to it. S is going to stand for the entropy in the system. So the disorder that will occur, the waste that is going to end up happening. So whatever calories are in this, you have to do, depending upon the temperature, you're going to multiply it by whatever disorder has occurred, and that tells you what your free energy is. And so this is going to be your available energy that you can do work. So this is going to end up being your free energy that you will now have. So every single time you go to consume food, you have to think of waste is also like all your normal body processes that are happening, but also just any of the stuff that you couldn't digest, the unusable energy that you can't do something with. And then depending upon the temperature, this can end up going and changing. And so this is how this happens when you go and break stuff down. This is what Gibbs free energy means in a biology standpoint. So again, H just means the enthalpy, which is going to be the energy available in the chemical bonds. S is going to be the entropy in the system, and so something that's all the unavailable energy that you just couldn't use for something, or maybe it's just, your normal body processes using it. And then T is the temperature in kelvins that you're going to end up having in K. And then G is just going to be your free energy. So this is what you actually have to utilize and to, again, be able to go and use within your body for something. So energonic and exergonic reactions you might have covered, but again, just in case, energonic reactions, you're going to be able to store stuff. Exergonic reactions, you are now utilizing that energy. So energonic always has to do with potential energy. Exergonic always has to do with kinetic energy, is the way my brain actually remembers it. So any reaction which requires an input of energy, and you are now going to end up having this, has what we call a positive G. It means you are going to be storing it. Anytime you are now using that energy, that's going to be exergonic, and so it's going to be a negative G. When you take, if you ever take higher level chemistry, there's actually equations that work with this that you have to do. They're more complex than this, but in general, that's the idea. If you end up with a negative G, that means that you're technically utilizing that energy. You have now a negative, you have a deficit. Any reaction which requires an input of energy would be the plus G, and you are storing it for any period of time. So if you are releasing the excess free energy, it will be the negative. If you're storing it, it's going to be the positive. And so that's what they're basically trying to tell you. So if you are releasing energy, you started with a certain number of reactants, and now your product is basically like you used everything up. Here, you started with a certain amount, but you're now supplying it, you're adding to it, and now you have even a larger amount of what you started with. So they're just opposites of each other, but it's the same general idea. So, activation energy is not free energy. On the test, for some reason, every year people screw this up. Activation energy is simply the energy required to destabilize existing chemical bonds and initiate a chemical reaction. In other words, if you want to turn on an enzyme, this is the energy needed to turn on the enzyme. So it's the extra energy required to destabilize existing chemical bonds and initiate a chemical reaction and to do something. And so it's any of the energy needed to basically turn on your metabolism or turn on your enzymes or some chemical reaction inside your body. So again, activation energy is the energy required to destabilize existing chemical bonds, and you're going to initiate a reaction. Enzymes are catalysts. So catalysts are going to be anything that's going to influence chemical bonds in a way that lowers the activation energy needed to initiate a reaction. And so enzymes make things go faster. They always do. And so instead of going and basically taking more activation energy, they actually make it so that you don't need as much activation energy when you use them. So again, the process of influencing chemical bonds in a way that lowers the activation energy needed, that's what catalysts do. And so they initiate reactions faster. And so that's what they're trying to show you is if you are going to be using an enzyme, you don't need as much activation energy to do something. If you are not using an enzyme, you are going to end up needing more energy to go and do the same exact reaction. So that's why when you were saying, let me just get back to it real fast, like when you guys were saying, what happens if you have a higher metabolism, this means the same thing. If you have more enzymes, it means that you can have a faster reaction, faster metabolism, because you don't need as much energy required to basically kickstart the whole process, and it goes faster. So, yep.
Can you repeat what a catalysis is?
Yeah, so catalysts are going to be something that's influencing chemical bonds in a way that you're lowering the activation energy. And so you do not need as much activation energy to initiating a reaction of some type. And so enzymes will always go and do that, and enzymes are catalysts. There are others as well, but generally speaking, we just use the word enzymes to describe this, and that's what the rest of the chapter is about too. But again, you are just going to be going and lowering the activation energy needed to do a reaction by using enzymes. The more enzymes you have, the faster the reaction can take place. And so this is how it ends up working. And so again, the more enzymes you have, everything goes so much quicker.